The mission is reaching its critical moment. Commander James Calvert faces a decision that will test both his submarine and his crew. The sonar operator checks the readings. The ice overhead is thick, dangerously thick. If they blow the ballast tanks and the sail doesn't break through cleanly, it could be sheared off like a bottle cap. But Calvert won't give the order to find thinner ice. He's hunting for specific coordinates, a precise spot. Because aboard the Skate, secured in a waterproof container, are the ashes of Sir Hubert Wilkins, the legendary explorer who spent a lifetime trying to reach the North Pole. Wilkins had died asking for the impossible, burial at the North Pole. The request went to the White House. Now it's Calvert's problem. A direct order to honor a dead explorer's wish while navigating one of the most dangerous operations a submarine can attempt. The gauge reads 12 feet of solid ice overhead. The executive officer watches the captain closely. Standard procedure would be to abort, to find safer ice. But Calvert's eyes are locked on the coordinates, the exact spot where Wilkins wanted to rest forever. The crew watches their captain. They know the risks. They know what he's choosing. Calvert orders the tanks blown anyway. Earlier that month, March 1959, USS Skate departed New London carrying an urn. Inside were the ashes of Sir Hubert Wilkins, a polar explorer who spent his life trying to reach the North Pole. His dying wish was to rest there. The request went to the White House, and the White House handed it to the Navy. Commander Calvert's orders said, scatter the ashes at 90 degrees north. But that was only half the mission. Skate also had to surface through Arctic ice 10 separate times in different regions. Each surfacing would validate emergency blow procedures for the Polaris missile submarine program. One mission, two objectives: ceremonial and strategic. Skate's sail, the steel tower that rises above the pressure hull, had been reinforced before the mission. Navy welders added half-inch steel plate to the leading edge and top. The engineering calculation was simple. Ice up to 3 feet thick, the sail could punch through. Any thicker, and the impact would crumple the structure, flooding the bridge trunk and forcing an emergency abort. 3 feet was the line between success and structural failure. Calvert and his crew would live inside that margin for the entire patrol. The ship's navigator, Lieutenant Commander Bill Lehman, plotted the course using inertial navigation. Gyroscopes and accelerometers tracked every turn and speed change, calculating position without any external reference. But inertial systems drift. Lehman knew the rate, roughly 2 miles per day. Under the ice cap, there would be no GPS, no stars, no radio fixes. After 5 days submerged, position error could exceed 10 miles. That meant they might miss the North Pole entirely and scatter Wilkins' ashes in the wrong coordinates. Lehman's job was to keep the drift under control and surface exactly at 90 degrees north. The control room crew rehearsed the surfacing sequence before they reached the ice edge. According to operational procedures, they would rise gently toward the ice canopy using carefully controlled buoyancy adjustments. Read the upward sonar to find thin ice. Blow main ballast to punch through. If the sonar shows ice thicker than 3 feet, hold depth and search for a thinner spot, flooding the negative tank if needed to drop back down quickly. The checklist was methodical, but every step depended on equipment that had never been tested under operational conditions. The upward-looking sonar was experimental. The blow procedure under solid ice had no precedent. Calvert ran the drill 20 times. He wanted the crew to execute it without thinking. The sonar operators stared at their screens, trying to read a signal that had never been tested under real ice. Skate's upward-looking ice sonar was experimental. No operational precedent existed. Here's what they were working with. A pulse fired upward at 12 kilohertz. Thin ice sent back a sharp echo in under 100 milliseconds. Thick ice? The pulse scattered, the return widened. Now came the guessing game. The operators had to interpret that pulse width and estimate thickness. Navy engineers claimed 20% accuracy. Think about what that means. A 3-foot reading could actually be 2.4 feet, or 3.6, the difference between a clean breakthrough and a crushed sail. They'd practice reading the scope for hours in controlled conditions, But under real ice, with the entire crew depending on them, they would have one chance to get it right. Arctic pack ice is not uniform. From above, the ice appears as a vast white expanse, but underneath the surface is far more jagged. The ice forms keels and ridges. Average thickness runs about 10 feet. Pressure ridges, where ice sheets collide and pile up, push keels down to 25 feet or more. Then there are skylights, melt ponds that refreeze thin, sometimes only 2 or 3 feet. Skate needed those skylights, but the sonar could not tell a skylight from a pressure ridge until the boat was directly underneath. The crew would spend days searching blind, hoping the next thin spot was real and not a sonar ghost. If the sonar read 3 feet, but the ice was actually 4, the sail would hit a solid barrier during vertical ascent. The impact force equals the boat's mass times deceleration, roughly 50 tons over a contact area of 30 square feet. The sail's leading edge would plastic deform, a permanent bend, and the shock would propagate down the pressure hull. The worst case was a weld crack at the bridge trunk junction, where the sail penetrates the outer hull. A crack there floods the bridge trunk in seconds. The crew would have no time to seal the hatch from below. The result? Emergency blow with a flooded trunk, loss of positive buoyancy, and a submarine trapped under ice with no way to surface. Even with nuclear power, operational constraints set hard time limits. While Skate's S3W reactor could run indefinitely, the crew could not. Air revitalization systems and oxygen reserves determined how long they could remain submerged. Under the ice, every hour counted against their life support margins. The boat crept at 2 knots, with sonar active, methodically searching for thin ice. Mission planners had calculated the risks carefully. If they spent too long hunting for a skylight at the pole, they would exhaust their safety margins for the long transit back. The nearest open water lay hundreds of miles away across the ice cap. No reactor meant no propulsion, no life support, and no way home. The clock was always running. The constraints stacked: sonar error of 20%, navigation drift of 2 miles per day, operational endurance measured in hours under active search conditions, ice thickness ranging from 2 feet to 25, and a sail rated to 3 feet maximum. Any one of those margins could be managed, but Calvert had to thread all 5 simultaneously. Find a skylight within sonar accuracy. Confirm position within navigation drift. Break through within structural limits. Complete the mission within operational reserves. And do it 10 times without a single failure. Because one failure would tell Congress and NATO that Arctic missile patrol stations were a gamble. The Polaris program funding depended on proof that surfacing under ice was survivable and repeatable. March 16, 1959. Skate sonar detected a skylight reading 2.5 feet. Calvert ordered the ballast blow. High-pressure air at 3,000 psi flooded the main ballast tanks, displacing seawater. The boat generated 200 tons of net positive buoyancy and accelerated upward at 3 knots. The crew braced. The sail struck ice at 30 feet depth. A sharp metallic crack echoed through the hull. The boat punched through, bobbing in open water inside an ice field. Calvert ordered deck crew topside for inspection. Within minutes, they reported back. The forward edge of the sail was deformed. 2 hull plates were buckled. Calvert ordered an emergency dive back to 150 feet. The crew secured the bridge trunk and inspected the packing gland, the seal where the bridge access tube penetrates the pressure hull. They found a slow leak. Not catastrophic, but steady. The chief of the boat estimated they were losing 5 gallons per hour. Controllable with the drain pump, but a sign that the sail had taken more load than the design margin allowed. The sail was weaker now. The next impact might crack it completely. Calvert knew the math. 9 surfacings to go. Each one would stress the damaged structure further. Navigator Schaefer plotted the position fix using the brief surface time. Inertial navigation had drifted more than expected. As they neared the pole, the crew worked to narrow their position in the final miles of the approach. Schaefer recalculated the course. Calvert searched the immediate area for a suitable lead in the ice to make the final surfacing. With the mission stretching on and the crew facing mounting pressure, time was becoming a critical factor. Calvert faced a decision: continue the mission, aware that the reinforced sail was under immense strain from repeated breakthroughs, or abort and forfeit the 10 surfacing proof of concept that the Polaris program depended on. He looked at the Wilkins urn secured in the torpedo room. The mission was not just strategic. It was a promise to a dead man. Calvert gave the order: continue north. The crew secured from surface stations, and skate descended to 100 feet, trimming neutral. Now the real hunt began. Sonar operators swept the ice canopy overhead, searching for the next skylight. Every ping, a question. Every return, a disappointment. The boat crept forward at 2 knots, sonar continuously scanning the frozen ceiling above. 10 feet of ice, a near miss. 15 feet, worse. 8 feet, close, but not close enough. 12 feet. The randomness was maddening. No pattern, no way to predict where a thin spot would appear. Hour after hour, the same ritual. Ping, wait, hope, nothing. Time was running out. The mission window was closing. The crew understood the stakes. Find the pole, scatter the ashes, prove the doctrine. Or run out of time and abort with nothing. Every hour that passed was an hour they'd never get back. The ice above them held all the answers, and it wasn't talking. The upward sonar transmitted a 12 kilohertz pulse. The pulse traveled at 4,900 feet per second through seawater, struck the ice underside, and reflected back. Thin ice returned a sharp echo in under 100 milliseconds. Thick ice scattered the pulse and widened the return, sometimes doubling the pulse width. The sonar operators measured that width on the oscilloscope trace and converted it to an estimated thickness. But ice is not uniform. Air pockets, brine channels, and density variations all distorted the return. The 20% error margin was not a calibration problem. It was physics. No amount of training could eliminate it. Every surfacing decision was a bet that the real thickness fell on the safe side of the estimate. When Calvert ordered emergency blow, high-pressure air at 3,000 pounds per square inch flooded the main ballast tanks. The air displaced seawater through flood ports at the bottom of the tanks. Each tank holds roughly 100 tons of seawater when full. Displacing that water generated 200 tons of net positive buoyancy across the boat's length. With skate weighing 2,500 tons submerged, the net upward force accelerated the hull at roughly 0.1 gravities, or 3 knots vertical speed. That acceleration continued until the sail struck ice. Then all that kinetic energy converted to impact force in a fraction of a second. The sail had to absorb 50 tons of force concentrated on its leading edge without plastic deformation. Any thicker ice, and the force exceeded yield strength. The steel would bend permanently. The sail was a steel tower 8 feet tall and 4 feet wide. The reinforced leading edge used half-inch plate welded to a frame of longitudinal stiffeners. The welds penetrated the outer pressure hull at the bridge trunk junction. That junction was the weakest point. When the sail hit ice, the impact shock propagated down through the frame as a compression wave. If the force exceeded the weld's shear strength, the weld cracked. A crack at the bridge trunk junction opened a direct path from seawater to the interior of the pressure hull. The bridge trunk would flood in under 10 seconds. The hatch above was already open during surfacing. No time to seal it from below. The result? A flooded trunk, loss of reserve buoyancy, and a submarine with no way to surface again. That was the failure mode Calvert had to avoid. Not just damage, catastrophic flooding. The skate carried emergency battery reserves and lead-acid cells for backup power, critical insurance for a nuclear submarine operating beneath the ice. While the reactor provided primary propulsion and electrical generation, these batteries represented the crew's lifeline if the reactor failed. Cruising through the Arctic darkness required careful power management. Propulsion, life support, navigation, and lighting all drawing from the ship's electrical systems. But searching for thin ice demanded even more: active sonar pinging constantly, slow speed for precision maneuvering, and continuous trim adjustments to maintain depth. The calculations were sobering. The crew had to balance their search time against their distance from open water, knowing that any reactor casualty would force them to rely on battery power alone for the long transit back to safety. Time and distance created the ultimate constraint, not because the nuclear reactor would fail, but because if it did, survival depended on reaching open water before the backup batteries died. No margin for error, no second chances under the ice. Inertial navigation used gyroscopes to track heading and accelerometers to measure speed changes. The system integrated those readings over time to calculate position. But every sensor has error. A gyroscope drifts 0.01 degrees per hour. Accelerometers of the era faced minute errors, often measured in fractions of a gravity. Those errors accumulate. After 1 day submerged, position error reached 2 miles. After 5 days, 10 miles. Under the Arctic ice cap, there was no way to correct the drift. No stars for celestial fixes, no radio beacons, no GPS. The crew had to surface, get a precise position fix using sextant and sun angle, then reset the inertial system. But finding thin ice to surface through was the whole problem. Every hour they searched added drift. Every drift mile increased the chance they would miss the pole coordinates entirely. March 17, 1959, 1900 hours. After 9 surfacings across the Arctic basin, Skate's sonar detected what mission records describe as exceptionally thin ice at coordinates 90 degrees north. Calvert calculated this was within the sail's remaining structural margin. The sail was damaged, but the reading was below the 3-foot threshold. He ordered the final blow. High-pressure air flooded the ballast tanks. The boat rose. The crew braced for impact. The sail punched through clean. Ice cracked and chunks fell away. The boat held steady in the ice hole. Calvert ordered deck crew topside. They climbed through the bridge hatch into Arctic air at -40 degrees, carrying the Wilkins urn. The deck crew wore wool parkas and gloves, no Arctic survival suits. The Navy had not issued them yet. Surface time at -40 degrees was limited to 15 minutes before frostbite risk became unacceptable. Calvert read a brief prayer. The crew opened the urn and scattered Sir Hubert Wilkins' ashes onto the ice and into the open water around the hull. The ashes drifted on the wind and settled on the pressure ridges. The ceremony took 12 minutes. 2 sailors reported numb fingers by the time they descended back through the bridge hatch. Calvert was the last man below. He sealed the hatch and ordered the dive. Skate descended to 200 feet and trimmed neutral. The navigator set course for the Greenland Sea ice edge, 400 miles southeast. The crew monitored power systems, ensuring sufficient reserves for the transit. The mission log recorded 10 successful surfacings across different Arctic regions. Each one validated emergency blow procedures under solid ice. Each one proved that finding thin spots with experimental sonar was possible. The crew secured from surface stations. The boat settled into transit routine. The Wilkins urn, now empty, was stowed in the torpedo room. The promise to a dead explorer was fulfilled. The proof for the Polaris program was complete. The USS Skate returned to New London on March 25, 1959. All crew safe. The sail was repairable. Welders cut away the deformed plates and replaced them. Commander Calvert submitted a patrol report documenting sonar accuracy, ice thickness variability, and sail impact tolerances. The report provided the first operational data on Arctic surfacing. Navy engineers used it to refine blow procedures and sonar interpretation protocols. The 20% sonar error margin became the baseline for all future Arctic missions. The 3-foot ice limit became Doctrine. Calvert's crew had turned experimental procedures into operational fact. Within 6 months, the Navy authorized Polaris missile submarines to patrol under the polar ice cap. Skate's 10 surfacing proof showed that emergency blow procedures worked reliably in ice fields up to 10 feet thick. Sonar could find thin spots. Sails could punch through without catastrophic failure. Navigation drift could be managed with periodic surface fixes. The Arctic was no longer off-limits. It became a strategic missile launch zone. Polaris boats could hide under the ice cap, surface through skylights to fire, and dive back into cover. The Soviet Union had no equivalent capability in 1959. For the first time, the United States held uncontested dominance in Arctic waters. Sir Hubert Wilkins' ashes rest at the North Pole. His dying request was fulfilled by a submarine crew who risked their lives to reach the exact coordinates. The ceremony on March 17, 1959, remains the first and only funeral conducted at 90 degrees north by a submarine. Wilkins spent decades trying to reach the pole by air and surface expedition. He failed every time. In death, the United States Navy carried him there beneath the ice. The mission honored one man's lifetime ambition and proved a doctrine that shaped Cold War strategy. Both objectives mattered. Calvert understood that. Skate's impossible feat changed everything. The Soviets couldn't ignore what Calvert had just proven. Submarines could own the Arctic. Within a few years, both superpowers were conducting under-ice patrols, probing each other's capabilities beneath the polar ice. The basin Skate had conquered became a strategic missile launch zone for the duration of the Cold War. Soviet boats scrambled to develop their own ice surfacing capability, but they lagged behind. American sonar and navigation technology, the same systems that got Calvert to the pole, gave U.S. submarines a significant multi-year advantage in Arctic operations. That advantage translated into patrol stations closer to Soviet territory and shorter missile flight times. The Arctic was no longer neutral. It was contested water, and Skate had claimed it first for the United States. Skate's reinforced sail design became the template for all U.S. Arctic submarines. Later boats received thicker plating and improved structural reinforcements, with design modifications that reportedly included enhanced shock absorption systems at critical junction points. The 3-foot ice limit remained Doctrine, but structural margins improved. By the late 1980s, the improved Los Angeles-class attack submarines were specifically designed to punch through ice up to 4 feet thick. The sail was no longer the weakest link. Skate proved the concept. Later designs refined it. Every Arctic-capable submarine in the U.S. fleet traces its lineage back to the half-inch plate welders added to Skate's sail in early 1959. That 20% error margin? Gone by the 70s. Multi-beam systems mapping ice thickness with sub-foot accuracy. Digital signal processing. Color-coded thickness maps in real time. Today's subs have it easy. But in 1959, Calvert's crew did it first with instruments that barely worked. Upward-looking ice sonar that evolved from Skate's experimental system. Operators who had to estimate every reading. Analog pulse width interpretation. No color displays. No certainty. Just find the thin spots, punch through, dive back down. Skate's mission was the proof that sonar could do the job. The core principle stayed the same. Later technology just made it easier. Here's what no one understood until Skate proved it. You could turn the Arctic Ocean into a weapons platform. March 1959. 10 deliberate breaches through the ice cap. No precedent for the sonar readings. No data on structural loads. No playbook for navigation under solid ice. Commander Calvert's crew did it anyway. Why? To scatter one explorer's ashes at the exact pole. But that ceremonial act established operational fact. Submarines could surface anywhere in the Arctic Basin, which meant they could launch missiles from anywhere in the Arctic Basin. The United States had just claimed dominance over the top of the world. A dying man's wish became Cold War doctrine. Personal and strategic. Impossible and done.